might be a repeat of some things that I have written in the notes. I'm just not going to look at the notes, I'm just going to go through this freely. Okay? So, a force that causes the movement of water. Now, there needs to be a difference in osmotic pressure from one compartment to another, though. We still need gradients. We need an osmotic pressure gradient. Or you're not going to give water a reason. Again, we're talking about passive transport, right? We need gradients in order for molecules to move from one compartment to the next across a membrane. We need gradients. So there has to be, from one compartment to another, if water is moving from one compartment to another, an osmotic pressure gradient, which we'll get to in just a second. Now, when it comes to osmotic pressure, this force, it is a pulling force. There are other forces that push. And so what does that mean? It means that wherever osmotic pressure is greater, that's the direction in which water is going to move. Water is going to be pulled into a compartment. Why? Because we have an osmotic pressure that's greater in one compartment than another. So it's a pulling force. It pulls water towards it. Again, I think probably most of you know this already. All right, I'm just going to rehash some things. We're going to build up to what we're going to be discussing in more detail in this lecture. Okay? Now, when it comes to osmotic pressure, what dictates osmotic pressure? What influences it? What makes it go up? What makes it go down? What dictates osmotic pressure is solute concentration. Such that as we increase solute concentration, we increase osmotic pressure, peak pressure. Okay? So now there is a greater pull on water wherever that pressure just went up. As we decrease solute concentration, we decrease osmotic pressure. Okay? And when I say solute, what am I talking about? I'm talking about amino acids, sodium, potassium, chloride, proteins. Those are the kind of solutes that I'm talking about. Something that's not water is in essence a solute. Okay? So if we had to take those words right there and draw something, I'm going to pick the blood. So there's a blood vessel. Okay? And this is the interstitial space, obviously. So we have our interstitial fluid here. We have plasma here. I'm going to put solutes in both of these compartments. So the dot is a solute. All right? Up until this point, well, never mind. Now, it's important for you to put the same number of dots in the plasma as I do. So quickly just count them and put them in. Just kidding. Just make it so that when you draw it, it's blatantly obvious that the concentration of solute is much greater in the way that I'm drawing it here in the blood. Doesn't necessarily mean that that's always the case, just what we're drawing here. Now, given the definition of osmotic pressure and solute concentration and how it dictates osmotic pressure, obviously osmotic pressure is greater where? Solute concentration is greater where? In the plasma. Do you agree? So we have a higher solute concentration. It's more concentrated in the blood, the way we've drawn it. And so because of that, we have a higher osmotic pressure. In the plasma, here, to be completely thorough, a lower solute concentration, and therefore a lower osmotic pressure. Do we have a gradient? Do we? Of course we do. There's a difference in osmotic pressure in one compartment versus another one. That, by definition, is what a gradient is. A gradient is a difference in concentration, a difference in pressure. So we have a difference here. Water is going to move in what direction, obviously? Which way is water going to move? Osmotic pressure is a pulling force. Wherever it is greater is where water moves, so obviously water is moving into the blood, into the plasma. Now, if osmotic pressure was the same on each side of these membranes here, in each of these compartments, water's not moving. The osmotic pressure difference is going to drive the movement of water. That is, if we're what, by the way? That's with the P. Permeable. Believe it or not, there are certain areas of your body, salivary glands, areas of your kidneys, where water is impermeable. It's very rare, but it happens. Next semester, I'm going to tell you how you make spit, and part of making spit is part of the salivary gland being impermeable to water. If it's not, your spit isn't made properly. I'll tell you how your kidneys regulate other stuff, and in order for them to do it properly, there are certain areas of the kidneys that have to be impermeable to water. Okay, so water is no different than any other molecule in your body when it comes to what we discussed earlier, gradients, permeability. Okay, so given that I have water moving across this membrane here, this blood vessel, from one compartment to the next, it's permeable. So we're just going to assume that it is. But I just wanted to remind you that we need permeability. Okay, regardless of gradients. All right? So far, so good? Just trying to, oh yeah, we're good. Okay, so far, fairly straightforward. And what we've drawn is this. This is what we distribute. Boom. That's what we distribute in that picture. All right? Now, when it comes to osmotic pressure, when it comes to solute concentration, actually solute concentration, we can measure it. We can measure solute concentration, and when we do, these are the terms that we use. Now, because when it comes to the fluids in our body, be it plasma, be it intracellular fluid, be it lymph, be it interstitial fluid, it's very dilute. Our fluids are at a maximum, maybe 93% dilute, or at a minimum 93% dilute. Most of them are about 98, 97%, meaning 97, 98% of the fluids in your body, most of them, water. Okay, plasma is about 93-ish. That's really dilute. Most of the fluids in your body are mostly water. And so because of that, we can actually use these terms interchangeably, because the values are nearly equal in a dilute fluid. Now, if we were a chemist and we had a beaker and we were making solutions that were 25% dilute, that goes out the window. The values will be very different. All right? So, in a clinical sense, when we talk about the body, this is human anatomy and physiology, we can use these words interchangeably because their values will be nearly identical. I typically use the word osmolality. Not that that makes me better than anybody else, not that that makes me more correct than anybody else, because there are labs that use the word osmolarity. It doesn't matter. Whenever you see either one of those two, you know it's a measured value. Measured value of what? Solute concentration. When I had x equals 100 and x equals 10 and y equals 20 and y equals 50, I was talking about osmolality. That's what those numbers meant earlier on in the lecture tonight. That's what it meant. The number tells you how concentrated a particular fluid is. Okay, solution or colloid. You know, words I can use freely, right? Okay? So, I don't care if you know the units. What you'll normally see on the exam is when I write osmolality, I will have, instead of kilogram, instead of all this, osmoles of solute per liter, osmoles of solute per kilogram of solute, I'll have something that resembles, I'll have this or this, but I'll get rid of the kilogram or the liter of solution, and you'll see this. It's milliosmolars, okay? That's what you'll see in a lab that you send off when somebody has blood work done. The lab gives you the value for the concentration of sodium. You'll see this as a unit. Okay? So when you see this, I'm talking about osmolality. Okay? Unit of osmolality or osmolarity. It doesn't matter. again, we can use them interchangeably. Okay? And those of you that take chemistry, and everybody here should have, you know this. You know what I'm talking about. All right? So again, it's a concentration value. So now we can add to this story here, osmolality. And so let's make sure we understand again what it is. Osmolality, or polarity, I should say, is a measured value. Value of solute concentration. I could have put the word osmolarity there. All right? It's a, just like again, height and weight. Measured values. All right? And it directly correlates with osmotic pressure and obviously solute concentration. So now we can add something to these words right here. Is that, if I had some foresight, you know what, I'll just write it again. It doesn't matter. I'm just going to write it again so it doesn't get too messy. Okay? So we're going to do this. As we increase solute concentration, okay, we have an increase in osmolality, which is the measured value for that. You can say that something has an increase in solute concentration, but until you measure it, you don't know exactly what it is. You can say that someone's tall, but until you measure them to be 6'8", you don't know exactly how tall they are. And so that's what osmolality does for us. And osmolality is very important clinically because there are normal homeostatic ranges for osmolality that you will have to know like the back of your hand forever from this point forward. Again, most of you. So increase in osmolality, increase in solute concentration correlates to an increase in osmotic pressure. So all three of those things are going to be in parallel with each other. As they go up, they all go. As one goes up, the other two are going up. And for the sake of thoroughness, obviously, we're always thorough here. As solute concentration goes down, osmolality, the measured value, will be smaller, and we'll have a decrease in osmotic pressure. Okay, so there's a direct correlation between all three of those things. Okay? Now, you have to know the normal value for osmolality in the body, specifically the blood and other places as well. So blood osmolality, although this would hold true for intracellular osmolality in most places, that's why I say initially blood. Because from one cell to another, depending on where we are in the body, it can be slightly different. But for right now, I want you to know normal blood osmolality. So if you take blood from a particular patient and the osmolality of that blood is measured, you should be within a normal range of between 280 to 300. That's the normal range. That is a homeostatic range. That is the range that will help ensure homeostasis within the body. You have to know that. All right? And it's in your notes. Okay? That's here. Boom. All right? Now what? Before we get on to the stuff that you're going to teach me, because we have all this knowledge behind us now, we're going to talk about one more thing, tonicity. People get tonicity and osmolality mixed up all the time. Don't. Tonicity is not a measured value. Osmolality is, tonicity is not. Tonicity is luminescence. Tonicity is comparing the osmolality between two different fluids. That's what tonicity, you cannot say that the tonicity of this patient's blood is 300 milliosmolars. You can't say that. That would be wrong. That doesn't exist. Okay? If we had to make an analogy here, tonicity would be, if we're talking about somebody's height, you can say that this person's taller than them. You know how tall they are? No. But you know that one of them is taller than the other. I'm comparing two different people. That's what tonicity is doing. You can use these tonicity terms, hypertonic, isotonic, hypertonic, if you are comparing two different compartments or two different fluids. It's the only time you can use these. All right? You are comparing